we will get into it. So, I also said there were some questions about when is the exam. My plan is currently that the exam is 1 week from right now. Okay. So if we can do that, we can get through all this redox stuff today and Monday, maybe some review of it on Monday of thermo and redox. Then we can do the exam on Wednesday, and we would have that last day of classes that Monday to do a comprehensive review, anything else that y'all wanted to review. Remember, the final is everything. So, everything. It's good for you. All right, well, how do you feel about the electrical stuff so far? About batteries and electrochemical, voltaic or galvanic cells, all this kind of thought. How do you feel about what we talked about so far? Any thoughts at all? If I do something like, let's say, what do we do here? Trying to think of a good one. Easy. What's going on here? What have I drawn? I don't even know if it would work this way, but what have I drawn if it would work? So, shorthand, right? Carol, what am I not drawing here? Okay, that's cell notation, she says. All right. And so this implies what?
I know the 2 lines of salt bridge.
Okay. So what do you mean is the salt bridge? I think you're picturing something in your head, and I'm wanting you to describe it for us. Let me put beakers in. Okay, so we've got one beaker, you said. And
I'll have one substance.
okay, well, it's copper. So what do you want me to put in this beaker? Like, do you want me to just try the copper 2+? Yes. Anything else put in this beaker? How do you want me to do the copper solid? Okay. Can somebody help her? Don't leave Kara just do this by herself. Come on now. Help the lady. Help the lady. Galvanic cells or voltaic cells, yes. A rod or a piece of solid, right? Okay, well, it's just like an electrode, basically. I'm just going to do it this way, right? Okay, and it's made of copper, you want to say? Okay. All right, cool. Now what? You want another beaker? All right, hold on. Let me make another beaker for you.
Gold rod.
Okay, let me do that. Have a gold rod.
Also have the gold.
Ooh, and what else is gold solution? Okay. Probably a lot of acid with it, but pretty perfect. Okay.
And then color in the middle. I can explain it, but it's, it's like, they.
Go back to what you started talking about. What was the first thing you said? What do you want to connect them with? With salt. Does that make sense? Okay, so your salt bridge is your thing that completes the circuit. Like it's huge, just packed full of something, right? Okay, cool. So let's do this with, I don't know, let's do with calcium nitrate. That was random. Could have been any calcium. Okay. All right. Cool. What else do I need? Is this going to work like it is? Is anything going to react like this? Huh? No. Why? Because the electrons can't get there, right? The electrons can't hop from the blue big, right? So what do they need? How do you get electrons from one place to another? A wire, yes. Like a wire. And then it will react. Yes? Okay, I'm going to have a question in a minute. I picked this random, okay? And I do not already know the answer to this. Will this reaction work the way I have written it? I don't know yet. Okay? So we're going to have to look up something called the standard reduction potentials for this reaction. Okay? I literally just picked the gold, the copper because we did it, and I didn't want to do silver again because we'd already done it. So I picked gold. Let's see if this would work. Well, how do we do that? All right, so here, that's where we're headed. So let's see, do we do this? We have flow charge, electrical potential difference. Y'all remember what that is? What is that? That potential energy idea? And how do we measure it with these things? What units? Voltage. Okay, so that's talking about voltage. We have a voltage. So that's what we're going to call the cell potential. Now for this one, this is the silver. So this looks a lot like our cell over there, right? Okay. See that it's 0.46 volts up there. See that? That's where we're headed today, is trying to figure out, well, okay, that's for copper and silver. What is it for copper and gold? Let's see if we can figure out this reaction. Yes? What am I going back to, sir?
Just a second.
Okay. Now, let's see. Right now, we're going to keep everything 1 molar for right now because that's our standard conditions, but we're going to come back to that and change that. Okay. So, the idea of standard potentials is that somebody's done a lot of the work for us, and they've set up tables again, right? Published data, but we needed some standardization, right? I was talking to my quantum class about this, and it depends. These voltages, you have to be really careful, okay? Because the thing is set, chemists like to set things at 1 molar concentrations, right? So we'll set up these electrical potentials at 1 molar concentrations, right? But remember that that'll include stuff like H+, right? So Miriam, let's say you are working on some new enzyme treatment later, okay? And you look back, right, and you're looking at these electrical potentials, right, that these chemists set up. How likely are where are you going to probably use these enzyme treatments in? So are you going to make them for people? Or for, you're looking at like enzymatic drugs for people, right? Okay, so what if your people, or do we want to make their pH 0? Why not? They're not people anymore. That when there's positive food, right? So we don't want to do that. right? So she has to be careful because if she looks in a biochemistry textbook or some other source for biochemical data, totally different set of books. Because biochemists will set this at pH 7 instead of pH 6. Okay, so you have to be really careful looking up these voltages. We'll keep them all at a chemistry standard for Gen Chem because it's general chemistry. But just know when you get to biochemistry, okay, it'll be different. It'll sometimes they'll be nice and they'll write E naught prime. Often they won't. They'll try E naught thinking everybody knows. Careful. Okay. All right. 25C, you could probably keep your biological units at 25C. All right. Now, what we do is somebody who has the textbook available, remember it's online, look up in the back, and there is a list of voltages. One of the appendices, probably L. And so we're going to look up the voltages. So let's try. Let me go find these. Find it, Miriam? Which one is it?
It is.
It is a. I remember random things. All right. So you have this table, right, with this voltage potential over there. Okay. Notice where the electrons are in every case on this table. Which side? Reactant side. Okay. Because these are also called reduction potentials. So in every case here, you're taking something, an oxidized version, you're stapling new electrons onto it, okay? And you're getting a reduced version out. Okay, in every case, this half reaction is a reduction. So let's look at ours here. So we have a copper reaction, right? No, let's not look at ours first. Let's look at theirs first, and we'll come back to ours. All right, so theirs, they have, what's one side, what's one piece of, and what's the other piece of? What are our half reactions in this overall reaction? What do you see being oxidized? What do you see being reduced? Zn, zinc, is being what? All right, so Zn is going to some other Zn. Tell me some oxidation states to convince me that this is being, you said oxidized? Tell me some oxidation states to convince me of that. Where would you like for me to put some oxidation states on mine? Let's go up here. Good, that's what I was looking for, Miriam, is that you know, it doesn't actually say that it's 0. Does that make any sense? I wanted to see that y'all remember that. Okay, why does she know that's 0? Yeah, because it's just, that's how it comes from metallic zinc. Make sense? Okay, over here you said? Okay, then where do you want me to put my electrons?
Side of the O2 plus.
All right, now there are multiple answers to what I'm about to ask. Why? How did you arrive at that answer? It's correct. So stay with it. But how did you arrive at your answer? And there are multiple reasons that we could say.
I think that like the Zn2 plus, you would add 2E minus to make it equal.
So you're doing charge balance, and that is one of the things you can look at. What's our charge balance over here? Total charge on the left is 0. Then we need total charge on the right to also be 0. Right? And it's not. It's 2 plus right now. So he's adding 2 electrons each with a -1 charge to balance that. Yes, that works. Okay? you could have also thought about it from a perspective of what's going on the reaction. And these electrons used to be on the zinc atom, and they fell off. Now we have to write them separately. Zinc 2+ ion and the 2 electrons separate. Yes, both of those would be ways to think of this. Okay, what else do we have going on in our reaction up there? I agree that this is our oxidation half reaction. What's the other side? We always have to have a reduction half reaction too, right? So what do you want me to write, Miriam? No. All right. So I think my chemists, we know what we mean when we start writing things, and maybe y'all don't see what we were trying to say. So what I want to do is I want to keep it simple for a second. Let's leave the 2 off for now. The 2 will come back in a minute. Okay? But think about a single hydrogen atomic center. Okay? So a single hydrogen is going to have on the left what charge? Okay. So see, that will keep it a little simpler because we can just think about every hydrogen in there is going to have a 1+. And on the right, I know that hydrogen comes as H2. I get that. Okay? But I want to think about not that. I want us to zoom in on one of them. Does that make sense? So we're zooming in on one of the atoms. Okay? What is its state over here on the right? I agree with that. So we're going to put H 0. Does that make sense? Okay. Now, what would you like me to do with my electrons? Yeah, why? What's your reasoning?
Because you're adding a negative charge to cancel out.
You like the charge balance idea too. Okay. Y'all see where we went with this? Okay, but now I'm going to bring in that 2. Okay. So you guys know, right, that H doesn't exist like this, right? It's actually a 2. Right? So then then I need to do this. And 3. Okay, so we're balancing equations, right? I gotta have 2's here. Or I gotta use the 1/2. That would also work. If the way I would have done this is I would have said H plus 1 E minus goes to 1/2 H2 0. Okay, but you don't have to. Fractions. I love the fractions. But didn't have to do that. I'll get rid of it. I know it's the F word, sorry. So right? Okay, so are we happy here so far? What makes you happy about this? What do we not have to do, Mercy, that often I will have to do? Something is good about this that I'm always yelling about. You got to check, make sure. Electrons are balanced. Okay, 2 electrons and 2 electrons. That won't always be the case. Okay? All right, the other piece that I need is to look up zinc. See what I did? Found the zinc, right? All right, Chelsea, what is the voltage involved for my zinc reaction?
Pull it up on. I can't see this.
You cannot see it? Okay, so what you want me to write?
Doesn't matter which way it's.
It does. All right, wait, hang on a second. Hang on. Will you say what you were thinking out loud, Owen, because it's extremely important.
Oh, positive.
Yes, it is. Well, but would you use more words to explain the conclusion you just gave?
Okay, so if zinc 2 plus electrons, zinc, and that charge is negative 0.761 volts, then the other direction must be the negative value. Right, C to C2 plus. See what?
Carson, say it again.
If the value is negative and going in that direction, the one that we have is going the opposite direction. That means flip the sign.
So you flip the reaction. This zinc reaction is exactly flipped from the one that's there. Agree? Right? Therefore, in doing that, the voltage is also exactly flipped. Okay? So what am I going to write right here for my voltage? Alexis, what you want me to write right here?
Positive 0.76.
0.7618, you said? Okay, beautiful. All right, well, let's do the other one.
Is the E cell or does that measure anything? The voltage?
Voltage. Yeah, hold on a second, we go to the top. See that right there at the very top? And Carson, if you're looking these up in engineering textbooks, they'll usually delete these. But do worry about your, we do actually usually work on this. Where's the hydrogen? There. Oh, they use. So, it's funny. Chemists don't want to use fractions, right? I told you geology, we use fractions all the time, balancing equations, right? And chemists don't like that until suddenly. Okay, actually then I'm going to use this as a, well, which one do we want here? Oh God, they made that more complicated than it needed to be. Wow. That's hydride. That's not the one you want. Okay, hold on, y'all. Be careful of this. God, they made that more complicated than it needed to be. How would you have written this? Better than they did. How would you have written it? Like, don't, y'all, please do not use this line. Don't use that. Because Carson just mentioned, what did you ask about, Carson? Yeah, because that's not our hydrogen. That's hydride, like if you talk about a lithium hydride battery, that is H with a negative charge on it, not a positive charge. We don't want that. We want H with a 0 charge on it, which is this. But how the hell would you write that? Why wouldn't you just write? Second. Why would you just write that? It's easier. So, sorry, if you had a physical textbook, I would tell you to write this in, right? Electronic, obviously, we cannot do that. I think I can highlight, right? I'll highlight. No.
How do you get hydrogen?
Pump more electrons on this. So, how do you get a hydrogen with a negative charge on it? Well, how do you do it with this? Plug it into the wall. You pump more electrons onto it. Okay? So don't worry about it. I'm going to talk about this a little bit at the end of the slide. Okay. So what do y'all want me to use for my voltage here? 0. Yeah? Okay. What do you think I would like to do? Please. Yes, you would. This plus this gets positive voltage of 0.7618 or 761.8 millivolts, right? Yeah? Yeah? Make sense? Right. Okay? That's the overall thing, how you do this. Go to the table, look them up, okay? All right. I just showed you guys the old guy way of doing this. I tend to write these this direction because this is what's happening in my cell. See, it's being oxidized, so I flip the blue voltage. Hydrogen is being reduced, so I keep the red voltage as is. Add it again. Okay? Is that how you learn it? You learned it the other way? Okay. Your textbook does it the other way, right here. They say, figure out which one is the cathode, get the voltage for it, figure out which one is the anode, and what the reduction would be if it were occurring, and subtract it. So they're going to end up getting the same answer, but the way they're going to do it is they're going to say, this one minus the original negative 0.7618 volts, and they still get positive 0.76. Okay? Does that make sense? Yes, Ellen.
So, which one is the, is it the one being reduced?
Okay, so what happens at an anode, y'all ask? How do we define it? What happens at an anode? You do need to memorize this, guys. Just memorize it. Or put it in a cheat sheet for now. Memorize it. What happens at an anode? Oxidation happens at an anode. Okay, that means that whichever one of these is our oxidation, oh, it's the zinc, right? Miriam told us earlier, right, that that's oxidation. So that one is the anode. So that's the one we're going to subtract. Does that make any sense, Owen?
Yeah, and then,
Yeah. I hate mnemonics, but I do actually use a mnemonic for this one. I just remember anox. Like the animal? Anox. So the anode is oxidation. What's yours? Okay.
Red cat and an ox.
Red cat. What are the, no, I don't know what they're doing.
No.
Okay, just picturing a red cat and an ox.
I've never
Okay.
used that. I actually just saw that.
All right, good. Y'all have it so far? Can you do this? Yes? Oh, good, let's do it. So what did we have here? What do you want me to write for my blue equation?
RC. AU.
No. I want half the X's. Separate them. No AU's in this one. AU's will go in the other. They'll go in the red. That make sense? Anything else you would like me to write? Y'all, why don't you say what you did here? Yeah? All All right, now what do I want to do for the other one?
Possible.
Six, what is it? All right. What do we get? Actually, yeah, that last cigarette. Did I do that in the head right? Let me check. Yes or no? Did it work? Did you check it?
That's close enough.
Ah, good point. Okay. This is a great place to talk about this, Mary. Thank you for asking that. So, when we did delta G's, you remember doing the delta G's, and we needed to multiply by our coefficients, okay? You remember that? You do not do that for these, okay? A couple of ways that you can access this. One is that you're not a chemist and you don't care why, just know that you don't. That's one option, okay? But there are reasons that you don't. Physics reasons, okay? Batteries are in parallel. So it increases amperage, not voltage. Okay, so it works the same way. You don't care how many golds are being reduced, right? Because they're all running in parallel. They're all in the beacons together. They don't increase the voltage, the potential. They just, back to when I was talking about how much water was coming over that waterfall, there's just more water coming over the waterfall. Okay, they don't actually increase the height of the waterfall, just the volume. That makes sense? Okay. The other way to think about it is there are going to be slides that are going to come in a little bit. I'm going to give you an equation relating negative delta G equals N times F times E. So the N actually comes back in that equation. Delta G equals NFE. The N comes back right there and it takes care of it in that place. Does that make any sense? So all of those are valid reasons here, okay? But just please don't. Do multiply your delta G's by coefficients. Do not multiply your E's. Does that make sense? Okay? Good with that? All right. So I didn't know when I do this if it was going to work. Do you think it's going to work? If we set this guy up and put a voltmeter on it, would we measure a voltage? Measure a positive voltage? Yes. If you set this up and you measure a negative voltage, means no, actually it would run the other direction. That makes sense? In this case, we got lucky, and it is possible. So we could, if we had a copper electrode and a 1 molar copper solution, and we had this is the hard part, a 1 molar gold solution. That's not easy to achieve. But if you could achieve a 1 molar gold solution, right, you could actually cause gold to precipitate. You could gold plate something using that. That's just by sticking a copper wire, copper solution. The 1 molar gold solution is easy to achieve. Okay? Happiness? Feel like we're getting somewhere, y'all? Remember that your book does it the opposite way that I do. They say take the cathode and subtract the voltage of the anode. They don't flip the equation around like I do. Okay? So either way, we'll get the same answer. Also, remember that we defined our standard hydrogen electrode as what we wrote over there with hydrogen. That is the standard. That's the zero that we defined. Okay? This is what's called our standard hydrogen electrode. That's what I'm talking about. We set up a standard at pH2. Right? And this is how you would actually build one. I had never even seen one. Actually, I had never even talked to someone that has seen it. Because you're bubbling 1 atmosphere pressure hydrogen gas through a pH 0 solution and applying electricity. What could go wrong? Right? So, yeah, I've never seen one. I don't want to see one. You ever thought about this? There's a note there for y'all that are going on to Orgo. Don't do that with your arrows in Orgo because it'll be wrong. I don't know what they're doing. That's straight out of the book. I don't know what they're doing with the arrows, but it's wrong. Okay? Anytime in chemistry you draw an arrow like that, a curved arrow with a full arrowhead on it, you are moving 2 electrons from somewhere to somewhere else. Okay? Not whatever they're doing right there. All right. Do what? Oh, I'm just telling you, that they get counted out all the time on Orgo exams. I graded Orgo exams, and I'm like, what in the hell are they trying to do with you? No, that's not what an arrow does. Okay, so, all right. Here they are looking up fluorine gas, right? Voltages, right? Does that make sense? Okay, now I want to talk a little bit more about this right here. What if we had set this up as our standard hydrogen electrode? I'm just going to run my wire on down into there. Just my wire, okay? And let's see, now I'm going to need that standard hydrogen electrode. We need a new tube coming in right here. This is just a tube, and it's bubbling in hydrogen gas. All right, I'm going to make some bubbles here for a nice explosive hydrogen gas. Okay, we've got H plus in here at 1 molar concentration, and those bubbles are H2 gas. Right? Make sense? Okay, let's look at how we would change this. How would you change the cell notation? Kara, what would you do? What are those? Do we still have this? We still have our cell bridge? Okay. Do we still have this and this? What is this right here doing? What does this big vertical bar right here do? Phase separation, right? Okay. Now here's the big thing. Do we have solid hydrogen here? No, nor anywhere else. Right? So this side is going to look different. Right? Because I don't have a phase separation. Y'all follow me on that? Kara? Good? All right. Yeah? All right. So I thought of that because those guys get used the same way. So they're going to look them up, remember, and they're going to subtract. I'm not. I'm going to flip whichever one gets flipped and flip the sign on that one and add it again. But it works the same. Really the same mathematics. Okay? And there's a bunch of things. So I looked at the exam. a little while ago, and right now I have these tables printed on the cover sheet. So you do not need to write down any of the tables. I'll give you the tables. All right. I would like to move on to this one, if y'all are ready, but I'm willing to slow up if we need to. Yes.
So like, stuff like the hot reactions for the voltage, is there certain ones that you need to categorize, like going, like just in general?
No. The only one that I would say is even worth memorizing is the standard hydrogen electro. H plus stage 2 is defined. Simply. But and the reason I say that is because it was so hard to find, right? Or just to know, oh, I don't even need to bother to look for that. It's going to be easy. Does that make any sense? But no, you do not need to memorize this. I don't memorize these myself. We look them up. Any other thoughts on that, Allison? Where do you get to see, where have you seen them beyond Gen Chem? Have you seen redox stuff much? We did it with my clients. Yeah, okay, PChem you may need it. Electrochemistry, I think, is going to be talked about more as y'all get, God, when will y'all be my age? Kara, when will you be 54? What year will that be? A long time from now? Okay. So I'm sure that the redox chemistry, the battery stuff especially, because our economy is shifting toward to battery power now. And so I think this will be more important in chemistry than in current. Hi, Owen.
So it looks something like that. 5%.
Now this has got hydrogen and gold. I took gold out, but yeah, if you had both of them, you could. Yes.
I know you just feel like it was just folded.
No, I was just taking the gold out of the equation and just doing a copper versus standard hydrogen plate. All right, onward. Let's get the picture.
Mary looked it up, 2060.
Do what?
You're 2060.
2060?
That's scary.
That's right.
I don't like it.
Of course, I would have said that, you know, when I was y'all's age, that 2024 was just not even, that's like maybe in a science fiction movie. Yeah, so, you know. Yeah. The year 2000 was forever away, remember? I turned 30 in the year 2000, so, you know, yeah. Yeah. Hey, y'all remember how to balance this? Everybody take a second, balance this with your neighbors. Make sure you still can. Probably want to write it, just to make sure. Y'all work it all out there so that y'all can help Sydney when she comes up to the board to do this one. Oh. You didn't practice that. And no. Also, as you're finishing up the balancing it, look down in the bottom right corner. And I'm giving you some preview of the types of questions that I like to ask on exams about redox equations. So down in the bottom right, there's a handful of questions that I might ask. Sydney, come on up, let's get this thing started. Yeah, please. Just write the non-balanced thing to start with, right? And then we'll start with those. All right, y'all think ahead now. What are y'all going to ask the city to do first before we try balancing anything? What are y'all going to like her to do first? It's going to be our key here.
What we call it?
Half reaction. Which one do you want to start with? Yeah, I don't care, anybody. Which one would you like to start with, Sydney? The 10 SN. All right, so what's the SN state on the left? True. What's its oxidation state? Be very clear. It is 0. So help her, tell her what to write here. Okay, then the arrow. And then on the right, what's the state of the SN? Okay, so put the SN2 plus. Now we have to figure out what to do with our electrons. Where do you want to put electrons here, y'all? Hey, Brady, talk to her to convince Sydney of it. Y'all gotta get her to write it. Okay. You see why, Sydney?
Yeah.
You tell me? All right, ask everybody. I'm sure there will be yelling if they don't agree, right? Okay. All right, cool. Y'all happy with that?
Yes.
Yeah? Shall we continue then? So that was a half reaction. Do we need another one?
Yes.
Help her. Y'all stuff out, Miriam. You know what it's like to be up there. Come on.
2 plus.
Oh, wait, careful. We did not go to copper solid this time, but we went to red copper, right? Yeah. Okay. Well, that changes everything then. What do you want to do here? Okay, let's see. So earlier, Mercy, who was it talking about? Were you talking about how we do the electron? How we would add electrons on one side of it? Why do we do that though?
Because it's,
Okay, so everybody likes the charge balance idea. So that's why they wanted to add those electrons here. Because your total is 1 plus over here, but 2 plus 1 negative here. That makes sense? Okay, are we happy with these reactions as written? You are? Okay. We can go forward then, but I'm not happy with them. Mercy, would you do anything else to this first? No, not that yet. We'll get to that. You're right. Kelsey, would you do anything else here? Is something bothering you about our half reactions? I would, but I want you to talk about why. You are exactly where I was thinking, but I need you to convince her because they weren't seeing that, Kelsey, and you were. Oh, wait. Our electrons are not balanced and they must be balanced, right? Yes, ma'am.
Wait, so we can be balanced and don't balance?
Simple question is always, okay? But one thing is, you're going to be answering the question here. many electrons are balanced. This is why we balance redox equations to see how many electrons are transferred. So if you get down to this question right here, how many electrons are transferred, and you look at this, you're like, choice A says 2 and choice B says 1. Oh no. Does that make any sense? I need a single answer here. Because in reality, there was an answer. How many electrons are transferred? How many moles of electrons per mole of reaction? There is a true answer to that. It's a singular answer, right? So it's not 2 for part of it and 1 for the other part. The electrons got to balance them, okay? You're right, it doesn't matter for the voltage thing, maybe what you're thinking. But that would be a shortcut, and I would not like to use shortcuts. So, after all that discussion, what do we need Sydney to do here?
Find bottom half fraction. Two frames, yeah.
Yep, and then just distribute it through. Hey, Cindy, would you do me a favor and switch colors for the next piece? Because somebody else back here, Mercy, said that you would like to do what?
Voltages.
We'd like to do the voltages part, right? Oh, maybe we need to consult the table? Okay. Very good. Switch over to the chrome tab. All right, now what do we want to do? How do you want to do this? Do y'all use Control F very much for HTML? Okay, Control F it then. What are we at?
That's
Did we find it? Aha. Which one do you want to use, Cindy? Okay, what do you want to write up there then? Beautiful. All right. Keep going.
Would you use battery then?
It won't matter because remember you don't multiply these guys anyway. Does that make any sense?
Yeah.
Okay. Okay. Now what? What are you gonna do? Add them. Beautiful. Add on. Somebody with a calculator help her out, please. Make her do it in her head. Don't add those in your head.
0.2
Careful, careful. I will probably count on for it, but technically positive 0.291. Because the 5, we don't have 6 digits on the second one. We only have 3 decimal places on the second. But I probably, but just in case. Beautiful then. Yeah. Good. Good.
Since we multiply the average by 2 on the original equation we put to the Sn plus 2.
I agree with this. I think that is a really big take home also, right? Because if you just balance this without looking at electron transfer, right, it would look like 1, 1, 1, 1. Yes. Now, if you look at charge, it would probably tell you that something is wrong. But God, this is 2 coppers for every 110. That's it. Yeah. And that could surprise you. Right? You're like, well, why am I getting twice the stoichiometry? Well, because of reasons. Okay. What was the answer to these questions down here? Two electrons for every SN. Agreed? All right. How many electrons per reaction as we have written? Still 2. Yeah. The way we wrote this, now if I wrote it differently, you know how much I love my fractions. If I wrote it as 1/2 SN, if I wrote it in terms of my copper, then my answer on that guy would be 2 electrons per SN, 1 electron per reaction as written. But here I would write 2 electrons per SN. I would also write 2 electrons per reaction. Depends on how you wrote the reaction. Does that make sense? And the question that I currently have on the exam says you can do it either way you want. Just be clear. So if you balance it with fractions, then you would give me that answer. If you balance it not fractions, you would give me that. Does that make sense? So I am going to have to look at how did you balance the reaction? Do your electrons match the way you balance it? Oh, and talk to me.
I don't get how you get you.
Well, all this, it's those are the 2. Those are the 2 electrons. These 2 electrons are they're the same 2 electrons. Just that one on the product side gets canceled out by one on the reactant side. Because they're not usually free electrons floating around in your solution. It's dangerous.
So like the electrons, just for SN, would just that's not part. And then for the whole reaction, what's not.
Once you balance it. The number of electrons that you got to balance your half reactions is how many electrons are transferred. That's the end. Okay? Happiness? Okay. Oh. So we calculated before in thermochemistry, we calculated a delta G naught. Remember that? What was our problem with delta G naught? When you figure out delta G naught, does it automatically apply to your reaction that you're looking at? Why would it not? Okay.
If it's going on standard.
What do you mean? Oh, and yes, that's where I'm going with it. Please talk more.
Well, your reaction is going to be at relatively standard conditions. So the non-standard conditions, we use it to graph your delta naught and
RTL and Q. Remember that? Delta G of your reaction actually is delta G naught, right? Plus RTL and Q.
Okay.
All right. Well, turns out Electro, it comes out the same way. We have to adjust for real conditions. So we know that if we have a positive voltage, it will be spontaneous. And if we have a negative voltage, it will be non-spontaneous. We're going to stick up on the idea of when really are those things positive or negative. If delta G is negative, what do you tell me about your reaction? It is the type spontaneous. If delta G is positive, what do you tell me? Or it's spontaneous in the opposite direction, right? But it's negative, it's positive. Wait a minute. What if delta G is 0? Aha. Okay. Next set of questions. Ready? Now, if my voltage is positive, what will you tell me about my reaction? Okay. And my reaction is? Agreed. It is spontaneous. What if my voltage is negative? What if it's a negative voltage? Oh, it goes the other direction, right? What if my voltage is zero? Huh? True. All right, back to the equilibrium. Aha. When your phone battery is at 0, right? Your battery is at equilibrium. Unfortunately, that's a bad thing because you don't want your battery to be at equilibrium because it's not going to do anything at that point. It's just weight, right? But the idea of equilibrium still applies. And so we can use E in the same way we use delta G, it's just with the signs backwards. Here's our equation for it. This one definitely wants to go on your cheat sheet. And also, pretty sure this one's on the ACS on the sheet also. Yes. So delta G equals negative NFE. Let's talk about the pieces of that. You know what delta G is. We can calculate delta G all day long, right? Y'all remember that? Well, now we know what E naught is, right? And F is a constant right here, called Faraday's constant. 9.648 times 10 to the 4th joules per mole volt. That leads in the question that I was asking a while ago, right? And we were trying to make sure that we understood how many electrons are transferred in the reaction is the end. That's why I made such a big deal of calculating the number of electrons. See these 2 electrons transferred here? So when she does this calculation, N equals 2. That makes sense? You're going to need to be able to do that. Balance the reaction redox, use the N to tell me what the voltage is. All right? So the delta G is negative number of electrons transferred times Faraday constant times the E naught of the system. Questions on this? Yes.
So the N in this case, on this one would be 1.
Oh, on this one?
Yeah, that one.
Yeah. I agree. Now, remember though, we do not multiply the voltages by the coefficients. We do multiply the delta G's, right? So if I do the delta G's for this one, I'm going to have 1/2 times the delta GF of SN2 plus and 1 times the delta G of copper, right? And that is actually going to balance out in the mathematics here with the -2 or the negative. Does that make any sense? Okay. Good? So, where am I getting this, y'all? Y'all remember this? I want to make sure. Kara, do you remember where this comes from? Okay. Lori, do you remember where this comes from? Yeah, well, it's in thermal, that's true. More precisely then? Right, okay, wait. Let's make sure that we've still got that. So you said if delta G is negative, then it's what? Spontaneous. If delta G is positive, then what? So, okay, so that means then if delta G equals 0, at equilibrium, right? Make sense? Therefore, then we could take delta G equal delta G naught plus RT ln Q, set delta G equals 0, Q equal K, right? And we've got 0 equals delta G naught plus RT ln K. Subtract RT ln K from both sides, you get this equation right. Agree? Yes? Good? Reminders on that. So I'm going to do a little bit of math here, a little bit of algebra, okay? I do this because I hate it when a textbook just says, oh, you can see how the algebra works here, and skips it and goes on. I'd rather see it working, but I'm going to divide both sides by F. Remember that F thing? Faraday's constant? Oh, I guess I didn't write it. All right. I'll do it over here then. So, we've got delta G equal negative Ln, negative RT ln K. Right? And divide by both sides by F. And I've got delta G over F equal RT. I'm going to move my ln K out here. Y'all okay with me doing that algebraically? You see why I can do that? Do you? Is that correct? You're right. So this makes more sense, right? So far, so good. What I'm doing is I'm just factoring that guy out. So RT. Is that okay? See what I did there? That wasn't the next step, the other two. That would be my delta G. Make sense? No?
Why is the R on negative?
Forgot it. Good catch. Should be. All right. You can plug the numbers in over here. We could do that. We're running out of time. But if you plug these in, you're going to solve for the same numbers that we got with the delta. It's just a numeric proof. This is too strong a term, isn't it, Brady? American justification, maybe? I think proof is too strong a term. I do not claim to prove things in that class. Don't like the term. Justify it. But we're going to get this idea that the E of a cell is the, see what I did here? RT, the numerator, F in the denominator. And where did our 2 come from? Your 2. Okay? And it would be whatever number of electrons is transferred in whatever reaction you're doing. Okay? So the E of the cell is RT over F, ln K. Right? Where did the negative go this time? It's because in that definition, it's the negative of delta G. Okay? Yes? Maybe? Maybe? So if I take it, and here I'm plugging in numbers for it, you will often see just this random value, right? And you're like, what crazy chemist? E of the cell is some random 0.0257 volts divided by N times natural log of K. Where in the hell did all that come from? Well, that number and the units for it are taking R, 8.314 joules per mole K, times 298 K, but your reaction might not be at 298 K. Hint, hint. Okay? The reaction on the exam might not be at 298 K. And then F, that's a Faraday constant right there on the bottom. Well, that gets that random number right there. You'll see this a lot of times in textbooks. I don't like to use it. I'd rather just plug in my actual constants instead of this random number that I don't always remember where it came from. Okay? I think it's safer to do this. And Miriam, if you're doing this in biochemistry, your number would be different anyway, right? Because y'all's standard conditions. I stole this idea from physics. Like you see these triangle ideas where they relate. They do it commonly with like, what is it they do? Like volts, amps, and ohms. They'll do a little triangle thing for how you solve them. Same idea here. Look, you can get from any corner to another corner value equation. If you've got delta G, use this equation to get to K. Or if you've got delta G, use this equation to get to the E. Right? Same from any corner. You got E, you can get to K. You should be able to calculate an equilibrium concentration from any of these. And Murph, that's a thing that y'all might see later. This right here is done a lot. Okay? So when we try to figure out equilibrium constants, actually in chemistry, you set up a cell and measure the voltage. Because that calculates the K. Make sense? Well, all right. We've always had all of our potentials set up with 1 bar or 1 atmosphere. Those are really close, and I am not actually sure what the official definition is right now. Okay, be careful of this. Those are slightly different numbers. 1 bar is almost equal to 1 atmosphere. Okay, so when you're doing your calculation, you need to know which one you're supposed to be using. Like, if you get something off the table that's set up in 1 bar, and you use another thing off the table set up in 1 atmosphere, it might throw your calculations off just a little bit. How significant is that? Well, it depends on how your equations are set up. But also, importantly, everything is set up at 1 molar, and it won't always be the case. As we saw with delta G, we would have to change it. Blue is spontaneous. If your reaction is spontaneous, you increase the concentrations of the reactants, it'll be more spontaneous. You increase the concentrations of the products, it'll be less spontaneous. Hey, what did we call this idea? What was this idea where if we increase the products, then you can shift back towards the reactants? Do y'all remember that guy's name? Le Chatelier's. This is Le Chatelier's principle, right? That's all this is, really. Yes. And of course, there's a reaction, a relation, just like our delta G of a reaction is delta G naught plus RTLNQ. The E, the actual voltage of a reaction, is the E naught minus RT over an F, LNQ. The reason one's plus and one's minus, do y'all know the history of electricity? Oh, they chose the wrong direction. They chose the wrong direction. Look, people were making laws about electricity, right? Faraday's laws and stuff like that. And they're looking at, they're thinking there's like this electric fluid flowing from one side to the other. There's no fluid. But they thought it was a fluid. They thought it was the, what do they call it? It's the vitreous stuff, the idea of the spark of life, like in Frankenstein. That's the idea. Victor in Frankenstein is doing alchemy, right? He's trying to apply the spark of life back to the creature. It's not ether, but yeah, it has to do with that discussion also. Well, they knew it was flowing. I don't know, let's pick a direction, and they picked wrong. So they think of things flowing from positive to negative, they don't. They flow from negative to positive because they're electrons. They had a big chance of this. That's fine. All right there, most of Monday will be review then. So come with your questions, ready to make up problems for yourself. Look at the problems in the book. Be ready to ask, like, holy cow, what if he asks this? What do I do? Okay, be ready. Hit me with your questions. Ask me your questions, Bridgekeeper. I'm not afraid. All right. Oh. Oh, no.
Last name, last this week. So,
Hey, we have homework.
I